Look at this MRI machine in action. The technology inside it, along with the lasers in your internet cables and the semiconductors in your phone, is entirely powered by the mathematics of quantum mechanics. The math behind these tools is highly predictive, yet physicists deeply disagree on what it actually says about physical reality. This diagram illustrates the core issue. The left panel shows a quantum system evolving smoothly and deterministically. Particles exist as flowing probabilities. But look right. When we measure the system, that smooth wave crashes into a single, sharp, unpredictable outcome. The probabilities vanish completely. This tension between smooth mathematical evolution and sudden, unpredictable collapse is the foundational mystery of physics. It tells us that the universe explicitly forbids a clean, classical understanding of reality. This chart breaks down quantum superposition. Before we look, the system is a blurry state of overlapping possibilities. When a measuring device interacts, it should mathematically entangle into that same blurry superposition. Yet human experience only ever records one sharp, definite outcome. Our instruments are not simply lacking precision, and we are not missing hidden information. The math reveals a structural break in the laws of physics, right at the boundary between the microscopic quantum world and our macroscopic daily lives. To resolve this paradox, physicists have realized they cannot have it all. To fix the math, they must choose which basic human intuition about how the world works they are willing to sacrifice. This diagram of an open pocket watch captures how early physicists tried to solve the problem. They hated fundamental randomness, so they proposed hidden variables, unseen mechanical properties working like invisible gears to predetermine the outcome before we even measure it. This hidden gear theory relied on a concept shown here: local realism. First, the padlock indicates that physical properties exist absolutely before we measure them. Second, the distance grid shows that no influence can travel faster than the speed of light. Look at the speedometer gauge in this next chart. In the 1960s, John Bell created a mathematical boundary. It tests exactly how correlated two distant particles can be if those local, pre-existing properties are true. The dial shows the absolute classical limit. Now look at the bottom of the image. When we actually test entangled particles, their outcomes are correlated instantaneously. They bypass the light speed cones entirely, pushing the dial straight into the red quantum violation zone. Bell's theorem turned a philosophical debate into hard physical evidence. It proves mathematically that a universe restricted by the speed of light cannot also be objectively real in a classical sense. At least one of those pillars has to fall. This table outlines the 5 major interpretations of reality. Since the classical pillars are broken, physicists use these frameworks to fix the math. Notice how they disagree entirely on 2 core mechanics: whether the wave actually collapses and whether the universe is deterministic. Focus on the left side of this diagram, the Copenhagen interpretation. Here, measurement is treated as a practical, unexplained postulate. The math says the wave enters the black box, a collapse is forced, and a single definite reality comes out the other side. The trade-off here is straightforward. You get highly practical, predictive math, but in exchange, you must accept that true, uncaused randomness exists in the universe. Now look at the right side. The Many-Worlds interpretation completely removes the collapse rule to preserve smooth mathematical evolution. Instead of forcing a single outcome, the wave simply splits into diverging paths. This restores a completely deterministic universe without any randomness. But the price you pay is steep. You must accept the actual existence of infinite, unobservable branching realities being created every fraction of a second. You must choose your discomfort. Either accept an unexplained, random physical collapse, or accept that everything that mathematically can happen physically does happen. The left panel of this chart offers another path, Bohmian mechanics. This theory restores a single, deterministic reality by insisting particles have definite positions at all times. They surf along an invisible, guiding pilot wave. But to make this work, you must explicitly embrace non-locality. You have to accept that rearranging equipment on one side of the galaxy instantly alters a particle's path on the other side. The right panel shows objective collapse. Instead of hidden waves, this theory physically alters the standard quantum equations. Once a superposition gets too large or complex, it hits a threshold and spontaneously jumps into a single state. Look at the top and middle sections of this hourglass diagram. This represents decoherence, the modern explanation for why quantum weirdness bleeds into the environment. When a quantum system interacts with air molecules or photons, its delicate phase relationships scatter and spread outward. But as you pan down to the classical mixture of blocks at the bottom, the major caveat appears. Decoherence perfectly explains why the blurry interference disappears. It completely fails to explain why one specific classical outcome is ultimately selected from that mixture. No interpretation protects classical reality. Whether it requires non-local spooky connections, physically altering the equations, or enduring persistent paradoxes, the universe demands a compromise. This table separates reality from science fiction. Read the top row. A very common pop science myth claims that quantum entanglement allows for faster-than-light communication or telepathy. The strict physical reality is much more rigid. Entanglement does produce bizarre correlations, but actually sending a usable message from point A to point B still strictly obeys the speed of light. This brings us to the pragmatic path. This diagram outlines quantum cryptography, computing, and sensing. Building these advanced technologies does not require solving the underlying philosophy. Engineers simply leverage the undisputed math of superposition and entanglement as functional tools. They treat the philosophical debate about what is real as entirely secondary to the mathematical output they can measure. These equations work perfectly to secure our data and run the modern world, functioning reliably regardless of the universe's true ontological nature. It comes down to which classical intuition you refuse to lose. For a single objective reality, you either rewrite core physics equations or accept non-local pilot waves. Trusting the unaltered math means accepting a universe that infinitely branches. Look at this final diagram showing the wave transitioning into root-like branches. Quantum mechanics is mathematically flawless, yet interpreting it remains our most profound attempt to understand existence, probability, and the emergence of the physical world. The equations tell us exactly what the universe will do. The interpretation asks what the universe actually is. The choice of compromise is yours.